at the bottom of the first page of your notes paper, there's a place for the first of a couple of alternative definitions for the derivative. So start by filling this in there. F prime of a is the limit as x approaches a of f of x minus f of a over x minus a. This is another way to write the derivative. It's another way to compute the derivative of a function if you have a function rule for it. It says the book calls this the alternative form. Like I said, there are a couple of alternative forms, and they both show up on the AP test, so you'll want to know both. So we can, just like we could use the other version, the original definition of the derivative to compute a derivative, we could use the alternate form too. So I'm going to do this, the part A example, and I'm going to let you do the part B example on your own. So here I'm going to use that alternate definition for the derivative to find the derivative of x cubed. So remember, anytime I want to evaluate a limit of a function that's not well behaved, that means if I try using substitution and I get a 0 over 0 problem, I have three main techniques that I can use. Try to factor and cancel, try to get a common denominator until I can factor and cancel, or try to rationalize the numerator. So to find the derivative of x cubed happens to be one where I'm going to factor and cancel. I'm walking through this one as opposed to the other one because it has a factoring that you might not remember off the top of your head. The part B I'm going to let you do, that requires rationalizing the numerator. There's your hint. So if I want to find the derivative of x cubed, I'm going to take the limit as x approaches a of f of x minus f of a all over x minus a. So let's show you where I am. I'm here now. F of x is x cubed, and f of a is a cubed. So here's my new expression once I've updated it to use the f that I want in this function. So the part you might not have remembered off the top of your head is how to factor a difference of cubes. So x cubed minus a cubed is x minus a times x squared plus ax plus a squared. So once I get that factoring, once I remember that I have that factoring pattern available to me, I can cancel out my x minus a's. I have the limit as x approaches a of x squared plus ax plus a squared. Now it's okay to substitute in because I won't have a divide by 0 problem. And I get a squared plus a squared plus a squared, or 3a squared. All right, this graph I have here is not the same as the graph that's on your paper. So we'll do two examples that are similar here. If I have a function and I want to find its derivative, my goal is to find a function that gives the slope of the original function everywhere. So in this case, this example, this f of x I have here, happens to be piecewise linear. That means the derivative is going to be piecewise constant because the slope of a line is constant. So if I focus in on the domain 0 to 1, and I ask myself, what is the slope of that line? I can find 2 points on the line, y2 minus y1 over x2 minus x1, and it seems to me that the slope is 2. Well, it doesn't matter where along the line I pick, here, or here, or here, or here, or here, the slope is 2 everywhere on that line segment. So if I wanted to make a graph of the derivative, I'm going to have the output values, the slope, my new y, my f prime values, be 2 for that whole part of the domain from 0 to 1. Maybe not 0 exactly, maybe not 1 exactly, but in between 0 and 1, the slope is 2, so I'm going to have this function have an output value, a y value of 2. If I look at the next line, I'll even change colors. The next piece of my piecewise function, again, I can compute the slope. The slope is, what's the slope? 3 minus 1, 1 over 3, so 1/3. So it doesn't matter where along that line I go, the slope is the same. The slope of a line is constant. So anywhere in that piece of the domain, my slope is 1/3. So I'm going to put a constant, a horizontal line segment here in my derivative graph. Up here, the slope of that line segment is 0. So I'm going to have a derivative value, which is supposed to be the slope, of 0. And in this part, I have a negative slope. I can compute that negative slope. It looks like, what, -1, 3 to 3. The slope of that line is -3, so my derivative for that piece of the domain is a constant -3. So finding those numbers, I hope it was clear how I chose those y values. It was the slope of each of those line segments. Lines have constant slope. The thing that's really interesting here is, what is the derivative right at 1, or right at 4, or right at 6? So we have to think back to what we remember from 2.1. A function has a limit at a place where the limit from the left equals the limit from the right. And remember that a derivative comes from a limit statement. The limit is h approaches 0. So a function only has a derivative at a place where the derivative from the left equals the derivative from the right. If you're gonna, that's not formal yet. We're gonna get to formal in a minute. But if you think about what that's gonna look like in a graph, anywhere your original graph is smooth. So places where your original graph has a corner, not sure what happened there. Any place your original graph has a corner, the derivative will be undefined because the slope from the left, the derivative from the left, is different from the derivative from the right. So that limit, in this case the derivative, cannot exist. So I'll leave this one up to you. Can you, over here, somewhere, make me a graph of the derivative of this function? Let's call this f of x. Make me a graph of the derivative. The derivative should be piecewise constant. And then can you figure out where you're going to have to leave open circles because the derivative is not defined, because the original function is not differentiable? Notice this is a typo. We should not have the word the here. Letter A should say graph f of x's derivative, or it could have said graph the derivative of f of x.